All right, Physics 30s, let's do question number 4 here on quantum mechanics. Particle with a charge 0.5 plus 5e and 420 times the mass of an electron is accelerated from rest through a potential difference v. If it attains a wavelength 2.4 AD negative 13 meters, then determine the potential difference v. Okay, a good way to start the problem is using the de Broglie matter wave formula. So we have h over mv equal to lambda. So what I can do here is I can figure out the speed. And so I'll do that first. So Planck's constant, the mass, now we have 420 times 9.11 e negative 31. And then we need to multiply that by the wavelength, 2.48 e negative 13. Use brackets on the denominator so you don't get a calc error. Okay, I get this, 6.987 e6 meters per second. Okay, now what I can do is that I have the speed, I can think about how this charge was accelerated. And so the definition of potential difference, which you can use a delta V, that's the change in energy per unit charge. Now the change in energy really becomes kinetic energy, okay? And of course the initial kinetic energy is 0, so really change in kinetic energy is really only the final kinetic energy. And so if I put this in here, I have potential difference, which they just show as V, so I'll just use capital V here, okay? That's equal to 1/2 mvf squared over q. So let's put in what we know here. We have 1/2 times the mass, which is 420, times 9.11 e negative 31, times that final speed, which we just calculated, and divide that by the charge here, so 5 times the elementary charge. And the calculation. What is this little leaf or something on there? All right, I get a potential difference of 1.17 E4 volts. Okay, let's try one more problem here. We'll do number 5. Okay, number 5 says, when electrons are sent through a double-slit apparatus, the distance between maxima is 3.5 millimeters. If the distance between the slits is 7 e negative 10 meters and the distance to the screen is 6 centimeters, then determine the wavelength of the electrons and the speed of the electrons. Okay, so in this question here, they're referencing using a diffraction formula. So lambda is dx over nl. Now you can use this only if theta is less than 10 degrees. So if you think about how the setup is, right? You have this double slit, you have a screen. Now the distance here, we term that L. The spacing of the maxima have an angle of theta, and that's x here showing that spacing, okay? The distance between the actual slits is the d value in the equation. Okay, so setting this all up, we'll just calculate the wavelength. Now it says here the distance between the slits was 7 e negative 10 times 3.5 millimeters. And distance between the maxima, so it's again 1 order of magnitude. And we have the L value, which is 6 centimeters. Now, if you're wondering about the angle here, you can see that the angle is probably fairly small in this case because it's the inverse tangent of 3.5 e negative 3 over 6 e negative 2. It's just off the side there, sorry, there we go. So you can calculate the angle and make sure it's less than 10 degrees if you wish. But if you kind of visualize it, it certainly is. Yeah, it's like 3.3 degrees, which is far less than 10 degrees. So this approximation is just fine to use. All right, let's do the calculation for the wavelength. So 7 e negative 10 times 3.5 e negative 3 over 6 e negative 2. All right, I get 4.083 repeat, 3 repeat, e negative 11 meters, which is about 4.1 e negative 11 meters. And then if we want to know the speed of the electrons, so for part B, now since lambda is h over mv, what we can do is we can just solve it for v. Little Thomson switcheroo with the lambda and the v. Remember that? 6.63 e negative 34 over the mass. It's an electron. And the wavelength, 4.083 e negative 11. And the calculation. All right, I get this number, 1.78, so we're going to go with 1.8 E7 meters per second. Okay, you can try out the other questions on there. There's only a couple left anyways. Thank you very much.